Hello. Good afternoon, everyone. My name is Shishao, and I had working at the Alibaba on DC network for more than 6 years. My co-president Kamini has been the lead DC product manager with Broadcom for more than 5 years. In this talk, we will cover following topics, where I will give a brief overview of Alibaba network design and the basic principle behind this network design, followed by our latest AI machine learning network, which also follow the same principle. I will talk about the achievements we have got, the challenges we are facing, and how we handle this with our vendor partners. And Kamini will talk about the solution details. Okay. Basically, there are 4 blocks in Alibaba network. The first is the design network, which leverages the SRv6 to build a backbone network of our predictable network service to meet the various demands such as stability, functionality, and cost, etc. The second one is our distributed edge cloud, which is more flexible and get closer to our customers. Yeah. The third one is DC network, which is also a key component of our predictable network service. Because many different service demands start from the network. Actually, this is our front-end network. Most of our service, such as storage, are hosted in this network. Yeah. The last one is the HPN network, which means the high-performance network. All these blocks, we are using white box and Sonic to get better and faster. Actually, this simple idea is our principle. That is, we are focusing on the open and simple network stack. In other words, it utilizes a single IP product stack, a single chip, merchant chip white box, and programmability both in control plan and data plan. Yeah. I will double-click our DC network and HP network. As shown, we can see in just last 6 years, we have deployed 3 generations large-scale working network. We start from the 25 gig storage network with 100 gig uplinks to the 100 downlinks with 100 downlinks and with 200 gig uplinks. Now we are deploying the 400 gig HP networks with 200 gig connectivity to the GPUs and 400 gig to the spines. Along this path, to achieve the high performance and the stability of the large-scale production network, we have done a lot of work. For example, we self-designed the HPCC congestion control, which uses the INT to carry the data plan information to get a better utilization of the link bandwidth, as well as the low queue and the low latency. In addition to high performance, the stability is also crucial for a production network, right? With Broadcom, we co-designed the mirror on job and mirror on latency to detect the network failure and take action as soon as possible in our production network. Now, upgrading to the 400 HP network, the new challenges are arisen that requires the large scale and the high performance on a stressful travel pattern. And it's also more sensitive to the network failures. I will talk about the detail next slide. Yeah, very large scale, right? The previous generation of a 3-stage cloud network actually is a hard manager and less performance for the AI training workloads. To be specific, the more hops means more complex load balancing, which is harmful for bursty, low entropy alien flows, right? Another challenge is multi-tenancy. The performance isolation and the security must be taken care of between the different AI training workloads and the different customers. Right. The second is high performance for the strategy for tracking patterns. AI training workload is different from the traditional workloads with much synchronous collective communication with item flows. Actually, this is very very hard to fine-tune load balancing in closed network, since the closed network is a rerunnable non-blocking network, which means different trap pattern, different connect maps require different path arrangement. It's dynamic. So that's why we need, actually, it's harder if we take into account the inedible link and device failure in a production large-scale network. That's why we need a new approach to get the fully utilization of our high bandwidth network. And Kamini will talk about this part. The last one is failure sensitive. Collective communication is more sensitive to link failures. One link failures may cause the entire train task to fail back to the checkpoint. That's why the single point of failure problems must be dealt with in the AI training workloads. Yeah, and this is my part. I pass to Kamini.
Thank you, Shishao. Hi, everyone. So I'll continue on what the proposed solution is for these such large AI training cluster networks. So as most of you are by now aware, for AI workloads, this job completion time is very critical. So as I think previous presenters also touched upon this topic, that how critical the JCT is, that, taking analogy to a relay race, a single delayed flow can impede the entire job completion time. And so the network utilization and the network, how effectively we use, becomes very critical. And also, as there are, he touched upon the very large-scale problem statement, right? So for this, a robust, high port density, high radix Ethernet switches are very essential with enhanced load balancing capabilities. So let me categorize into 3 buckets the solution space. So one is the high bandwidth and high radix switches. Broadcom's latest 51.2 tera Tomahawk 5 switches, which is right now in production, is the highest bandwidth in the industry. And by having high bandwidth and high radix, this helps achieve flatter topologies and hence significantly lesser switches and overall TCO reduction. I'll give an example to walk you through how this is achieved with a high bandwidth switch in the next subsequent slides. And by having a flatter network, it's also easier to do the overall network management, like easier to manage the network, easier to do congestion control, and so on. The second category I would like to touch upon is the intelligent load balancing capabilities. So here, we'll be introducing 4 subtopics, like the dynamic load balancing and reactive path rebalancing and the global load balancing and fast link failover. I'll explain in the subsequent slides as to what these mean. The third bucket, as he said, multi-tenancy is important in the AI backend network as well, and we have multitude of features supporting this and making this possible. And plus, the telemetry is an equally important part in making sure that the network is monitored constantly for any glitches or anywhere you can have a granular visibility into the queue depth and so on. And that enables the self-healing network. Okay. Let me talk about how the high bandwidth, high radix switches help here. So doubling the bandwidth it is actually helping with the 6 times reduction in the switches. I'll show you how. Say you have a cluster of, let's consider a small cluster of 256 GPUs. Using a 25 tera switch, in order to be able to connect all the 256 GPUs, assuming there is no oversubscription, you will need at a minimum 4 TORs. So I'm representing it like 4 boxes, blue boxes here, all are 25.6 tera switches, each connecting to 64 GPUs totaling 256. And in order to make sure that the TORs are connected, we need at least 2 spines. So that brings the total number of switches to 6, right? And this is assuming the common GPU NIC connectivity is a 200 gig port. And this will actually mean this, the 6 switches actually translates to 153 tera of switch capability, as well as a lot of interconnects that goes along with that, right? Now, if you just think of it, this gets collapsed into a single big switch, high radix, high bandwidth, 51.2 tera Tomahawk 5 switches, production ready today. And this shows an example of a 256 by 200 gig port density, where this helps connect all the cluster of 256 GPUs using a single chip. By doing this, what do you achieve? You are essentially flattening the network from a 2-tier to a single tier. So the moment you flatten the network, there are lesser number of switches involved, lesser number of optics, interconnects, less power consumption throughout because the number of switches are getting reduced, and the need for the rack space, the rack needs is also less, and the total cost is also becoming less because your number of switches is reduced. And because it's flatter, you can do a much better congestion control mechanisms can be employed. And of course, it also improves your latency tremendously. OK. Let me go to this topic of the enhanced load balancing capabilities. So before I touch upon this dynamic load balancing, let me just give a 30-second refresher on how the traditional ECMP works, right? So the ECMP, the traditional ECMP, is based on the static hashing, like using the 5-tuple hashing and the modulo operation. This has been excellent so far, very reliable mechanism, no doubts. But this does not take, the traditional ECMP does not take the port loading into account, which means how much the port is congested. That information is lacking. And this could lead to short-term imbalances in your load distribution. And if your hashing entropy is low, this could lead to polarized load distribution, essentially, right? In order to remove all the short-term imbalances, dynamic load balancing, what we have introduced here is basically you can select between your egress links based on the local congestion quality. We call it as a path quality metric. And this path quality metric is a function of queue size and port loading. So what it does is basically it redistributes the flow based on the member loading, and the flow gets redistributed only after the inactivity timer expires. So you do not run into the issues of packet reordering as much as you think you would. Now, the next topic is actually taking this DLB one step further. We call this as the GLB, or global load balancing. So what we have done here is, by taking into account the path quality metric, the same congestion quality metric parameter of the next hop node, what happens here is, for instance, the 1.1 has visibility in the ECMP table of what the path quality metric of 2.2 is, so that it can make decisions on where to even forward it to begin with, to make sure you choose the non-congested path or uncongested links. The next is the reactive path rebalancing. So here you are probabilistically reassigning the path of if the current path is deemed not optimal, or if the current path is seeing congestion. And then fast link failover. So here, of course, as Shishao was talking about how the failure points, whether it is link failures or device failures, becomes very critical in AI network. So here what happens is, if there is a failed link in hardware, it automatically steers it to the next link. And this is done at less than 500 nanosecond time. Okay. So net-net, the key takeaway from this is making sure that the network that you are dealing with for your AI backend infrastructure, as long as it has the best network utilization, the link utilization, that means you are looking at lowering and lowest tail latency, And that means that your JCT is significantly improved. And that's what makes it very, very, very critical for your AI workloads. All right. Then talking about, I don't have a specific slide on multi-tenancy since it's a very familiar topic. But we do have the EVPN VXLAN capabilities in our switch, which can help with the multi-tenancy. And for when coming to the telemetry topic, I think Bhaskar and Surendra touched upon this extensively in the previous presentation. So basically, the in-band telemetry, the IFA, it enables optimal AI workload processing by providing granular visibility into the queue depth. And we have seen that the in-band telemetry provides better performance compared to the DCQCN, which is the standard approach. And using IFA, the ROCKY sender will be able to dynamically adjust the flow rates in the AI workload to ensure minimal queue buildup that could happen in the network. The second one is the packet drop, the hardware accelerated mirror on drop, packet drop monitoring. So this will essentially, with all the, no network is free of packet drops, as we all know and understand. So this mod enables expedited root cause analysis in case of failures, and it heals the network, through automation. All right. To summarize, so based on our close collaboration with Alibaba and multiple other cloud customers, the key takeaway here is we are looking at AI-enabled silicon with an open stack like Sonic layers, with all the great load balancing and high bandwidth and other features, good features, multi-tenancy and telemetry features, along with the orchestration layer. Like this is the unified, the software stack. And the key point here that I would like to call out is this is all open standards-based Ethernet fabric. And this is all using merchant silicon. There is no vendor lock-in, no proprietary technology involved. This is merchant silicon and white box running on simple open networking community stack. That's all I had.
Thank you.
It's not a question, but comment. Shishao, great job. Thanks for your support and collaboration. Appreciate it.
Thank you.
Any more questions?
Yeah, simple one. Just wonder, why do you always stay with the class topology?
Because
thoughts? If you look at the InfiniBand side, right, high HPC side, right, there are many topologies to choose from. Have you ever exercised different topology and see what happens?
Yeah, I think it's also mentioned in the Ziping talk about the actually today we have the focus the closed network, not only just the because we have the principle, right? I talk about that we focus on the open and simple and large scale in all cloud service topology. This is why today we focus on the closed network, and also cloud network can do the non-plugging forwarding, right? But we choose the right approach to do that. I think this is a simple answer. Yeah.
Right, but the thing is, it's not simple behind. The cloud started when we're dealing with the cloud, east-west, right? Now we are in the world of AI. I think you should take a look at some other topology, and I can work with you.
Thank you. Thank you.
What do you suggest?
Thank you.
What is the topology you are recommending?
I think Jeff knows what I am talking about.
Yeah, I recommend take it offline. Maybe a talk for.
Okay.
Sure, let's connect.
It's a full mesh. You want to take a look. Other topology are also good.
Okay. Thank you.
Okay, last question.
Yeah. So the question, can you talk about the resource requirements for switching from local load balancing to the global load balancing?
For me?
He's talking about the performance, the test.
It's ongoing.
It's ongoing.
We do see the benefit for the DLB and GLB protocols. But today, actually, the test is ongoing. We have not finished yet. Why? Because actually, this approach is much different compared with flow-based, right?
I guess my question is more for Broadcom, because you're switching
Okay.
local load balancing to the global load balancing. You have to track more congestion.
Yeah, we are
the people
doing.
to track you, because you have to track the whole path, right? The next hop.
Correct.
You're not tracking the local
Yep.
resources. So you need more resource to
Correct. That's right. That's right. We are in the POC and working with multiple cloud customers on this, and we are collecting results. Right, Surendra, do you want to elaborate?
I think the question is about the resources, and the resources, like it's a one stage look ahead, and the number of resources.
only one stage.
No, like it's daisy chain. Of course, you can go to 3 stages. It's a three tiers.
3-tier.
Yeah, 3 tiers.
Five
Yes.
hops,
Yeah, so it's a 5 hops. It goes ahead. So the switches, like you can see, the commodity ASICs that are being used, it has enough scale to do this 3-tier topology.
Do you have a number for this?
I don't know whether that's out yet, but yeah.
Yeah, the testing is.
I think this is a deep dive. I recommend taking it offline. Thank you very much. And I think, sorry, we're out of time.
Okay.
Thanks a lot,
Thank you.
guys.